David Smith here with another flipped classroom math lesson. A few tips before we start. First, remember that you can speed up or slow down the playback if that helps you follow along. Second, you can turn the captions on and read my words on the screen. Third, you can pause the video at any time to catch up with your notes or write down questions for class. Today's lesson covers number sequences. And this is an introduction to a new chapter that we're starting this week. So check this out. Here is a definition for a number sequence. It's a list of terms, which are numbers, because that's a number sequence, in a defined order. So it's not just random terms. There is a rule that these terms follow. So a list of terms in a defined order that follows a specific rule. And so that rule can be used to predict the next term, or the 50th term. We can jump right ahead to do that as well, coming in a later lesson. So let's take a look at four possible sequences here. We have 2, 4, 6, 8. That's a sequence. I think you can see what the rule might be. What is that rule? Plus 2, right? We're just adding 2 to each term. Now here's one, 14, 11, 8, 5. What's the rule for that one? Minus 3 each time. We're just subtracting 3. Take a look at this one. What would be the rule for that? 1, 3, 9, 27. Okay, if you notice that each term is the previous term times 3, you're right. We just multiply the last term by 3 to get the next term. Finally, take a look at this sequence, has a different pattern. What might that be? Okay, if you notice, these are all perfect squares. So this is 1 squared, that's 2 squared, 3 squared, 4 squared, and so on. So these are just 4 examples of the kinds of sequences that we'll be dealing with in this chapter. Now before we move on, I want to point out one thing here. Notice how this sequence doesn't have the ellipsis ending. So that means this sequence is finite. It ends. And this sequence, the ellipsis indicates that this sequence just goes on. We just keep applying the rule to get the next term. So this is infinite. All right, so let's take a look at some vocabulary and then let's get a little bit more detailed with a specific sequence. So first off, U sub 1 is just a notation to represent the first term. So in our sequence here, 2, 4, 6, 8, U sub 1 is just 2. U sub 2 would be 4, sub 3 would be 6, and U sub 4 would be 8. And indeed, I've put those 2 down here. Okay. UN represents the nth term. So that's like a general term. It's like we could solve for the nth term using some math a little later. But UN is like the nth term. Finally, N is the term's position in the sequence. So it's really clear here that this would be the second term, first term, and so on. So N is the term's position, where it falls in our sequence. So we took a look at U1 and U2, 3, and U4. So what would U5 be in that sequence? If you said 10, you're right. And then U6 would be 12. Okay? So now, think for a minute. This is a critical thinking step. What would UN be? So it's going to be some formula here that uses N, so that if you want to know the 18th term in the sequence, you would just plug 18 in for N, and that would tell you what that term is. So think real hard for a minute, pause the video if you have to, and then come back. Okay, let's see how you did. You'll notice that term 1 is 2, term 2 is 4, term 3 is 6. So what we're doing is we're multiplying the term number by 2 each time. 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, 4, the fourth term times 2 is 8. So this would just be 2n. So this means that if you want to know the 97th term, you just multiply 97 by 2, and that will tell you what the 97th term of this sequence is. Very handy. We'd hate to have to go 2, 4, 6, 8, 10, 12, 14, 16, counting along and make sure we got it right to get to the 97th term. That's much harder than just using that formula. So let's take a look at a few more formulas. 2 types of sequence we will discuss. Arithmetic sequences The same value is added to each term to get the next term. That's an arithmetic sequence. A geometric sequence, each term is multiplied by the same value to get the next term. So let's take a look at two examples. Here we go. Here's an arithmetic sequence. We're subtracting 1 each time to get to the next term. So that's arithmetic. This one is geometric. We're multiplying by 2 each time to get the next term. So geometric. This relates to something that grows geometrically. It grows faster and faster and faster. It creates a curved graph, whereas an arithmetic sequence grows in a linear fashion, creates a straight line graph. Okay, what I've done here is put up a couple sequences, and I'm prompting you to figure out the term formula for UN. So pause the video real quick and see if you can do these. Do both of these. Find out what you have to do to get each term on that one, and the same for that one. Okay, so I've put a couple sequences here. 3, 6, 9, 12, and I've put 1, 4, 9, 16. Both have the ellipsis, so these are infinite sequences. They go on as long as we need them to. And what I'd like you to do is pause the video and come up with the term that goes here, the little formula that helps us get from term to term, so we could quickly calculate, say, the 12th term of this sequence or the 18th term of that sequence. So pause the video and then come back. Let's see how you did. So you can tell that this one is just multiplying the term number by 3. So term 1 times 3 is 3, term 2 times 3 is 6, term 3 times 3 is 9, and so on. So the formula is UN equals 3n. Pretty straightforward. Now this one's a little bit more tricky. Hopefully you notice that every single one of these numbers is a perfect square. So that means that we square the term number. So 1, first term squared is 1. Second term, 2, squared is 4. Third term, the 3 is squared is 9, and so on. So now we have two formulas that would help us easily calculate the nth term of these two sequences. All right, let's take a look at the other two sequences and figure out their formulas like we did before. So these are a little bit more tricky. I think it's pretty easy to see that this sequence is decreasing by 3 each time. Sweet. But how do we use n, like the term number, to get our terms? So if n is 1 for the first term, how do we get 14? By subtracting 3. So we start with 17 minus 3n. Now think about that for a minute. If n is 1, first term, then we're doing 17 minus 3 times 1. 17 minus 3 gives us 14. Let's test this on the second term. So 11 would be 17 minus 3 times 2 is 6. 17 minus 6 is indeed 11. And if you keep testing it on, this will give you the formula for whatever term you wish for that sequence. So you can see this is an arithmetic sequence changing by the same amount each time, and there's our formula. So in some ways, this chapter, one of the tricky bits is to be able to look at a sequence of numbers and figure out what the pattern is that's driving each term from the last. Okay, now this one is even a little bit more tricky. I want you to think real hard about it. This involves exponents. Our nth term is going to involve an exponent. So take a look at these numbers and see if you can figure out what the pattern is. Okay, if you notice that they're all powers of 3, you're on the right track. This is 3 to the 0 power. Remember, anything to the 0 power is 1. This is 3 to the 1, 3 to the 2, 3 to the 3, and then so on. So our form is going to have 3, and then it's going to have some kind of an exponent. So how do we get 1 out of a power of 3? That's 3 to the 0, but our term number is 1. So what we do is we do 3 to the n minus 1. So that means that for the first term, you have 1 for the first term, minus 1 is 0. 3 to the 0 is going to give us 1. Second term is going to be 2 minus 1 in my exponent, so that's 1. 3 to the 1 gives us 3. Third term, 3 for third term. 3 minus 1 is 2. 2 squared gives us 9 for the third term, and so on. So it's thinking like this that cracks the code for finding these formulas. All right, let's do a few examples. So take a look at this sequence. First, decide, is this arithmetic or geometric? And then once you've got that answer, come up with the UN formula for that. All right, so if you notice, that we're just adding 3 every time. So that makes this an arithmetic sequence. And then the formula is just 3 times n. So first term, number of the term is 1, but to get 3 we have to multiply that by 3. And then second term, 2 times 3, we get 6, 9, and 12. So that's our first one. All right, let's try this one. A little more tricky. 3 minus 12, positive 48, minus 192. So first off, arithmetic, geometric. You answer. Okay, if you said geometric, you're right. There's no way we can get this sequence of numbers by adding or subtracting the same term each time. So we're going to go geometric on that. Now, formula. This one's a little bit more tricky. If you want to see if you can crack the code alone, pause the video and do that. I'm going to walk you through some steps that help you find that. Okay, so the first thing to notice is that we're multiplying by -4 each time. 3 times -4 is -12. -12 times -4 is positive 48, and so on to get 192. So that's a little bit more in the guts of this formula. It confirms that we're geometric because we're multiplying by the same number. Happens to be a negative number. Now, coming up with the general term formula is a little bit more tricky. But here's what we need to do. We're going to multiply by -4 each time. So I'm going to go ahead and put my -4 in here. Okay? Now, I need to figure out how would I get 3 by multiplying it by -4. What I would do is I'd do n minus 1 and put my 3 out there. So what this is remember, the first term, this goes to 0. -4 to the 0 is just 1. Anything to the 0 power, doesn't matter if it's negative, positive, pi, whatever that number might be, it's just 1. So times 3 gives us our first term. Now let's test this for the second term. So we have a 2 for n. So this becomes 2 minus 1, or just 1. So -4 to the first power is just -4 times positive 3 gives us -12. And if you test this out, you're going to find that you can generate each of these terms. So just remember that some of these are tricky. Now I want to point out a pattern. When we have an arithmetic sequence, we tend to multiply our n in some way to get the next term. When we have a geometric sequence, we tend to have an exponent for our n lives in an exponent. So that's a general pattern that you might want to exploit. All right, let's try another one. 2, 10, 50, 250. Geometric, arithmetic. Think about it. Okay, geometric. There's no way we can get the next term by adding or subtracting. So again, we have a geometric term, or a geometric sequence. So now, what would be a formula for that? So if you look at those numbers, think about what you're multiplying by to get the next term. And you'll notice 2 times 5 is 10, 10 times 5 is 50, 50 times 5 is 200. So we're multiplying by 5. So I'm going to get this out here. Here's my 5. Now, how am I going to use 5 to multiply by something to get a 2? Remember, it's the same little trick here. N minus 1. So 5, like 5 to the n minus 1 for term 1 is going to be 5 to the 0, which is going to be 1. So we can just pop our 2 out here. And that gives us 2 for the first term. Now let's test this. Second term, n is 2. 2 minus 1 is 1. 5 to the 1 is 5. 5 times 2 gives us 10. And if you test this on out, you're going to find that this will generate each term for you. So again, now a general term formula for this one is that. All right, let's try a really tricky one. 1/3, 2/5, 3/7, 4/9. Okay? Now, when you take a look at this and try to figure out whether it's arithmetic or geometric, it's pretty tough. It's hard to see what's going on there. Am I adding the same thing? No, probably not. Am I multiplying by the same thing? Hard to see. So in this one, we're going to analyze to find the general term formula and then see what that tells us. All right, so what I did here is I just brought the bottom part down because what I'm noticing is that I can figure out that I'm going to add 3 each time to some number because here's my 3. 5 is 2 plus 3. 7 is 4 plus 3, and 9 is 6 plus 3. And so my next bottom is going to be 8 plus 3, or 11. My next bottom is going to be 10 plus 3, or 13. So what I've done is I've sort of deconstructed these bottoms to get this sort of constant thing happening, which is my 3. So now I can rearrange this a little bit. I'm going to write n over 3, comma, n over 3 plus 2, comma, n over 3 plus 4, comma, n over 3 plus 6. So now it's starting to look like a pattern. The 3 is constant, okay? Nice. My n is just my top. That's good. So now what do I need to do to get this 2 and this 4 and this 6 from my term number? So think about that real hard. Maybe write the next step in the sequence. Let's see what you get. All right, so here's the trick. Check this out. Over n, we're under n. We're multiplying this 3, we're adding 2 times 0 to that 3. This 3, what we're doing is we're adding 1 or 2 times 1. That's adding the 2. Under this 3, we're adding 2 times 2. And under this 3, we're adding 2 times 3. So now I've got something going in here with a regular thing. I've got 2's everywhere. So I've figured out a way to kind of re-represent this. Okay? So make sure you get what that is, because I'm going to erase and we're going to start over again with another board. All right, so I've reproduced our sequence here, and I reproduced that last step that we did on the last board down below. So check this out. We're just basically one step away. We just need to replace this with some term that involves n, and then we're done. Because then once I have an n here, a constant term, then I can just plug in my number for n, crunch the numbers, and that's going to give me my formula. So check this out. In order to get 1/3, this has to go to 0. So we have 2 times 0. So how could I make this term be 0? Think about that for a minute. Check this out. It's going to be n over 3 plus 2 times n minus 1. You see that? So this makes this 0 because this is first term. So 1 goes there for term 1. There we go. And then we're over 3 plus 2 times n minus 1. So it's 2 times 0. So this part goes to 0. So we would just have 1 over 3 for our first term. Let's just test that. Actually, we don't need to test that. This is our general term formula for that sequence. Now, to get full points, you're going to need to simplify this because I have a bunch of stuff going on here that I can do that with. So let's get an n on top. I'm going to do 3 plus 2n minus 2. 2n minus 2. Now, can we simplify that anymore? So the last step, super simple. We have a 3 and a minus 1. So let's make that n over 2n plus 2. And there is our formula for the nth term. Okay? So this formula is neither geometric nor arithmetic. You can see we don't have any powers here, so we're not geometric, and we don't have a straightforward multiplication. The top is growing, the bottom is growing twice as fast as the top, but we're also adding 2. So this is not good. This is going to be a neither geometric nor arithmetic. Now that you've finished the video, take a moment and jot down some notes or questions for our next class. Remember that you can also watch the video again if you want to increase your understanding. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.